Topics about future energy, robotics, and recycled water. Our first speaker is Professor Wang. In Chinese, we call him Wang from School of Engineering, University of California, Irvine. Professor Wang received his bachelor and master degrees in mechanics and engineering science from Peking University. And he earned his PhD degree in mechanical engineering from Pennsylvania State University. He is an famous expert in PEM fuel cell, lithium air battery, and other energy systems. His topic is Polymer Electrolyte membrane fuel cell for vehicles. Let's welcome Professor Wang. Wang, next 30 minutes all yours.
Dr. Su, for the introduction and also the invitation. My name is Wang. I'm from UC Irvine, and I'm working with renewable resources life and mechanical aerospace engineering. I'm from UC Irvine, and you can find my information from my website. Today I will present something which is very exciting, clean fuel cell technology, and for automobiles. So again, this may represent some kind of over $1 billion of investment, not only from the government and also from private, and especially in the state of California. Let me just briefly go through this figure. This figure shows the car powered by fuel cells. Okay. And this is the hydrogen gas station network in the state of California. And you see somewhere in color, which means there are more than 2 hydrogen gas stations available. So if you are lucky, living in this area, and you are okay to buy a hydrogen fuel cell vehicles. And the last one figure shows the machine learning and the artificial intelligence that we apply to clean fuel cell for automobiles. Well, first of all, I would like to introduce UCI, and especially our mechanical and aerospace engineering, the clean fuel cells. And then we'll go over this kind of the fuel cell vehicles and hydrogen gas station. Like I said, there will be over, I would say, $1 billion or $10 billion investment in the next 10 or 20 years. A huge opportunity. Now, I will cover some briefly fundamentals, technical issues there, and which UCI and have some original contributions to this technology. You see University of California, Irvine, we are, and I want to highlight this slide because at UCI it was a kind of a finding in 1965, and as today is roughly about 57 years old. So it's kind of similar with why I think they call more 60 years. And in 2 years or 3 years, we're going to celebrate our 60 years birthday. So again, there is some, I think, a connection here. So we have University of California, we have 10 campuses. And UCI is as the second youngest campus, and founded in 1965. And we have 5 campuses in the Southern California and 5 around this kind of the San Francisco area. So that's basically the part for UCI. And we are actually fast growing, and I think in the past 57 years, and we worked hard, and we now get into the public university top 8. And we are still working on our kind of USUs for engineering ranking. And we have some kind of the very good ranking for money and American dreams, and some kind of top 10 core university school. And again, there's some other kind of the parts here for the ranking. For mechanical and aerospace engineering, and we are very active and support this kind of undergrad education, especially for this kind of entrepreneurship and innovation. So this figure shows us our students fund external funding from companies, airline, or Orange County, and they build this kind of the competition. I think this kind of the it's called hollow loop engine. So that in discussion with the nowadays the richest person in the world, Elon Musk. This is kind of summary of my department. We were founded in 1983, and in 1990 we have this aerospace engineering into our department, and we have the master and the PhD bachelor degree offered, and we have a number of the people either NAE member or the fellow professional society. And we have a few centers like I mentioned here. This is energy and advanced power. So let me go to the next one. So UCI, I put some ones here. Number one in the US for sustainability. And we also have some core school. And actually the one criteria is for this clean energy or energy efficiency. So there's some historical reason here. And we have our Nobel Prize winning research led by Professor Roland, who actually discovered depletion of ozone by this kind of freon refrigerant. So which called this kind of ban of this freon in our residential refrigerant. And with this kind of historical reason, and you see I support this energy reduction, clean energy, and we have some kind of the first Congress, and this is from the official use UCI side. And this is the bus is the twin fuel cell power vehicle bus, and we bought about 7 or 8 years ago, and as our campus bus. I will give more details when I get to the twin fuel cell technology. So go back to this technology here, and this device very novel, innovative, and possibly can change the world on how we utilize our energy. Like a Tesla, right? And now go back here. So this device, so if we replace this device by a battery, okay, and instead we use a chemical inside of the battery, we put the hydrogen gas, we put air into the battery, and this battery will produce power. And then we release those kind of the water to the environment, okay, it will be clean. So again, that's the advantage here is we use hydrogen as primary fuel. And hydrogen is renewable, right? And it's hurting when I drive from Irvine to this nice 4-star hotel here, conference, because the gasoline price is hurting in the past 2 months. Right? I think it's 30%, 40%, right, increase. Now, the reason is because of this kind of dependency. And there's a war somewhere, there's some tension in the world, and the price can change almost every day, every moment, and fluctuation. So if we working with hydrogen, what becomes clean, what becomes renewable or sustainable, right? Well, depends on, especially the renewable resource solar, right? And will be pretty much independent of those kind of the price change. Even there's a war between Russia and Ukraine, the price will be the same. And most exciting, okay, and the Department of Energy, US, and has a target for $1 per kilogram hydrogen within 10 years. So what that means, so if you basically your current driving range, 300 miles, you need 5 kilogram hydrogen. So you need only to pay $5 for the fuel. So again, that's the benefit for hydrogen. Another one is the efficiency, 65% peak efficiency in practice, and 80% in theoretical theory. And 50% is normal in the driving efficiency, over 50%. And again, low temperature operation, minus 30 to 100 degrees C. They easily scale up, just like a battery, put it one by one, and you can put a million solid state for high power. So again, there are a few issues here, I listed here. Some things also for the application. You can see the fuel cell is looking for a replacement of battery. Right? In our cell phone, even the mouse, if you have a hydrogen fuel cell to power your mouse, and then you need to change your battery in certain containers. Because you can have a hydrogen tank cartridge plug-in, which is more kind of a energy intensive. Then you go to the next slide here. So it's not some ceramic, and there is a real stuff going on. And this is structure, material. And again, there's challenges. So again, when there are challenges, materials and innovations, and we need some funding. And there will be funding investment coming into this technology. And there's also this kind of a fuel cell stack, another 5 kilowatt stack, developed somewhere a company. And if we know the operation principles, we can design a transparent fuel cell, and we can observe what's happening inside. So again, that's part here. So 2 years ago, we provide a review paper, this figure from the review paper about the fuel cell automobile or vehicles number of 2016. You see, 15 there's a little bit, and 16 there's a lot. I think it's kind of steady increase. So this figure was prepared 2020, I think in January. That's why we won't see any increase to 2020. But I was told I think it's over 10,000 last year. So it's kind of trend is a steady increase. So this is prior to 2010, and we have fuel cell bus, and showing the government support for clean energy. And there's also a few kind of the bus and the vehicle here. And especially for this bus, okay, and all are operating in the state of California because we have hydrogen gas station. And this is also funded by DOE, and this is rated around the technical ratings, which means if you want to buy it, you don't care about the money. Okay, you can buy it. Okay, you can drive. Okay, so again, I'll go maybe for more details. So this is the one I think is off the shelf. You can buy from the Toyota official site. Okay, and this is second generation. And I think 2020 last year they launched their second generation with highlights. And you can see a few numbers I put it over here and showing the improvement. Okay. And now the range goes to 400 miles per charge. Okay, so again, this can be extended to 1,000 miles very easily, and we just need to find space for hydrogen tank. Okay, so if we double the tank, the size of the tank, this can be doubled. So again, you can compare with the battery, and it's impossible. You need to pay more money to double the battery pack. So with that, let me see here. Okay, I can go to the next part here. So this summarized table some sort of the popular fuel cell vehicles and their configuration and their mileage, okay, MPG equivalent. So you can see the city, highway, and combined, and it's in city drive, it's even more efficient compared with freeway. So I think there's a code startup ability that we're going to cover. And there's also some kind of a fuel cell bus and their configuration. And or I use a pure hydrogen. I believe I put somewhere. I think fuel tank capacity is about here. Sure, for each kind of vehicle, normally if it's a light duty vehicle, 5 kilograms. This is comparison, something with 1 year operation at UC Irvine. And we have this number for hydrogen fuel cell bus versus a diesel ICE-based bus. And so this input needs this amount of hydrogen for 1 year operation. And we have this kind of tons of air put in the vehicle. And this hydrogen fuel cell produces water and some unused oxygen and nitrogen. And versus if it's diesel, ICE engine, or internal combustion engine, and there's tons of production, even the PM, which is some sort of air pollution resources, and the NOx emission. So again, this is something, we have this nice old summary, and they shoot the government, and the government will support fuel cell bus technology. This is details for UCI's. The first, I think, UC campus hydrogen fuel cell bus. And we have this one, and this is some detailed configuration, 200 kilowatts. This 260 miles range, and the 37 seated and 19 standing passengers. And again, this bus serves millions of students, and parents, and campers. I was told this year we're going to retire this bus because it's almost a service time for what's to be retired. 7 to 8 years. To support this hydrogen fuel cell vehicle, and we need this kind of somewhere, I think, covered by title here. This is hydrogen fueling station. So again, it's very similar to a gas station. We have everything about there is similar, and this is the hydrogen gas station. We have a dispenser. We have some hydrogen in near storage, hydrogen ground. And because the hydrogen won't expand, there needs some kind of physical change, like heating or cooling. So we need some kind of the cooling chiller facility to cool down the hydrogen storage tank. So, and this is showing this kind of the hydrogen gas station price. And this is supported by the state of California for some sort of analysis. So again, if we build as a 1 or 2 hydrogen gas station, the price will be huge, okay, per hydrogen gas station. So if we heat up for a high kind of the station capacity, like it's 1500 kilogram per day, which can support 300 vehicles, okay, which is a normal standard, and the price is not so high. So again, it's durable. Like I mentioned, the DOE will support, invest over $1 billion in the past, in the following 5 to 10 years, to invest hydrogen hub, which is very likely going to be in the state of California. Okay. So next slide, I will show you this kind of a figure here. This is Irvine, this is San Francisco, this is Los Angeles. Okay, you see, this shows this kind of a high number of hydrogen gas station customers in the state of California. So if we go from here to the rest of the United States, and there is only 1 or 2 hydrogen gas stations available. And in the United States, only the state of California support hydrogen gas station, support fuel cell technology. So again, so if you are somewhere in this colored candidate map, and I think you are okay to buy a hydrogen fuel cell vehicle, because you can find a place to charge or fuel your vehicle. This shows up the world effort, not only US, California, and there's Germany, Japan, South Korea, China. They put a lot of money into the hydrogen infrastructure development and also fuel cell technology. And again, this is the state of California, and for year by year, the number of the retail stations for hydrogen. And I was told there will be 100 somewhere. I think it's in schedule plan by the end of this year. So move forward here, I want to give some cold start ceremony. This is rare for Southern California because we never have kind of freezing kind of winter. But again, we still can know if you go skiing during the winter, right? It's kind of frozen there, and you need to start your vehicle in a frozen condition. And for fuel cell, we have this cold start operation challenge barrier. So again, the fuel cell needs the water to function, the membrane to conduct proton. So we work first under sub-freezing temperature, right, as low as minus 30 degrees C, and we measure the ionic conductivity of the membrane. Okay, so under different temperature, different water content. So this is our early work. And we also use the neutron imaging or radiography to see the water production during the fuel cell operation. You see this water accumulate inside the fuel cell with time. Okay, so again, this is, if this is vapor, this is water, liquid, right? It can be recharged from the electrolyte or fuel cell. But if it's ice, it's gonna stick inside, right? You can think about it, keep going, and what's gonna happen here is this kind of the voltage. You can look at this voltage as a battery, right? And it's a kind of the first is steady, and then once there's too much ice inside the fuel cell, we will block oxygen transport to the reaction site, and then the voltage is going to drop to zero, which means fuel cell dead. So here, that's our work. So we do have some kind of fundamental and also original contribution and analyze and see how those kind of the code start are related to the fuel cell or electrical design. And what's the major physics there? And what's the parameters of the play around? Okay. And this is the time scale or time constant we provide. This is to facilitate the hydrogen kind of fuel cell development to overcome this kind of environment. So we have some of the physics showing this kind of ice formation physics impact with some neutron radiography, high efficiency, and we also have durability study to improve code start performance. Somewhere I want to miss is this machine learning, AI for fuel cell. So the idea, sorry, for fuel cell, if we want to apply, and there's some material we want to optimize, and in the application side, and we want to make sure it's environment, good durability, high performance. So instead of use some kind of very complicated model, and then where you see in practice there are always some uncertainty, and we want to use this neural network, right, by learning, and then we apply the learning parameters to apply to this kind of vehicle and the bus design. So that's the key idea. And we do have a number of publications applying this kind of the neural network CNN to analyze the neutron radiography images and to capture the water distribution and water content inside the fuel cell. So this is one application. Another work when we did is here. We use the AI control, use the genetic algorithm coupled with the neural network, and to do optimization and to find the maximum power from a fuel cell at different operating conditions. So again, this kind of identification will provide a control unit, which always going to control your fuel cell operating at the maximum power, right, under the specific operating condition. So another work called, my life is working on force flow field optimization. Again, this is show this structure, and this is show this flow. And this flow provides hydrogen and oxygen to fuel cell. And we have this kind of we call this kind of SVM, this kind of the sector, the support vector machine. This is another machine learning methods, and coupled with this GA method, and we identify the configuration of the force meter structure and to output the best performance of fuel cell. So with that, let me conclude. Okay, first, fuel cell have been successfully commercialized in vehicle application, and the hydrogen gas station network is required to support this kind of fuel cell worldwide commercialization. And cold start is crucial to fuel cell vehicle application. And we have show a few kind of example for machine learning and AI application to fuel cell R&D. That's all. Thank you.
It's a very fantastic presentation. I do believe the hydrogen cell fuel car might change the vehicle market in future. And right now we have 3 minutes for Q&A. Please don't hesitate to ask questions.
My question is regarding your safety. Do you have any safety concern when you use hydrogen with your cell?
That's a very good question here. And just maybe bring back to this kind of the safety concern to the hydrogen tank. I think I do have this kind of the number here. And if you pay attention here, and we have the hydrogen, I think the pressure tank, the pressures are around this 700 atm millibars. Okay, so it's very high. And with this kind of pressure, the tank can hold sufficient hydrogen fuel to support this 300, 400 miles driving range. So for this kind of a pressure is high. Okay, and however, I think that we can provide technology to support, to make sure the safety is under control. I think this first, the people use this kind of carbon fiber, right? And give this kind of additional strength to the fuel tank. So this is one part. I think technology-wise, this will be 100% okay. And it passes DOE safety kind of the code. So the second one is the hydrogen fuel cell vehicle actually was tested more than 20 years. Okay. I think I know there's a first, I think one of the first one tested UCI in the University Hill, in the residential area, and our factory is able to release fuel cell vehicle and drive and the cameras, but we need to assign some kind of a safety issue, the reliability issue. So if there's any accident, for example, hydrogen is told and hurt or killed the driver, and then fuel has no liability. So again, during the past 20 years, after those single accidents. So that's why I would say I think it's very safe to use. And again, in terms of this technology, I think it's our human being and our technology R&D companies, I think we make it happen to take this 700 atm pressure, make it safe for our customers to drive. Thank you.
Any more questions?
Thank you. Wonderful presentation. Thank you very much. I have a quick question regarding comparing to normal electronic vehicles like Tesla and some kind of hybrid vehicles like Volvo Volt. What are the advantages of hydrogen fuel cell car compared to electronic vehicles like Tesla? Because right now Tesla is so popular now. Thank you.
Thank you. This is a very, very good question here. I think that's also a question fuel cell automaker face these projects. And if we trace back to 10 years ago, 15 years ago, and when there's no kind of a charge station available everywhere, and the battery vehicle faces the same challenge as fuel cell. Right? Another day, the Tesla succeed. And if I go back to this is the infrastructure. If I go back to the technology, so we all have this kind of oil dependency issue. We see the price, right? And if you pay attention to Tesla, the price increase possibly. I was told at least I read some news increase, right? And battery technology, we may face another material dependence problem. Okay. Again, so that's one issue here. Another issue I think the testers are facing is for longer driving range, right? For a heavy duty application. Right? So again, so if you want to double your driving range, you will drive tens or thousand miles per fuel, right? Per tank. And for hydrogen fuel cell vehicle, you just need to double your hydrogen tank, which is very cost effective, not going to cost you much money. But for battery testing, you need to pay double the money because it needs to double the battery. So again, there are other issues for this kind of the safety issue about burning, the self-burning combustion, those issues. I don't think that's going to be critical. I think again, R&D can solve this problem without any challenge, major challenges. Thank you.
Because the time limit, we have only one more question. Oh, so many questions. Okay, two more.
Thank you, Dr. Wang. That was a wonderful presentation. So I'm an environmental scientist, a water resources engineer, and I was wondering, obviously, hydrogen is a completely clean fuel, but are there any environmental impacts from the production of hydrogen cells or the disposal of hydrogen cells that we need to be thinking about?
For hydrogen, I think safety is an issue. For environmentally, I would say the current technology, hydrogen production, I think 80% is still from fossil fuel. So we call this kind of I think the methane shifting reaction. So this makes this hydrogen price very low, about kind of $2 per kilowatt. And I think the DOE, the Department of Energy, US, they're looking for some hydrogen production from renewable resources, for example, solar and wind. I think if we get to that stage, and we can 100% eliminate this kind of carbon dioxide, get involved or footprint in the hydrogen production. For others, I don't foresee any environmental impact because hydrogen itself is very clean, and if there's some leakage, and it's very reactive, it's can combine with oxygen, it becomes water. Yeah, I would say in this kind of a concern, I think it's 100% I would say environmental friendly.
Okay, only one more question. Please ask in short and answer in short.
I have a question for Professor Wang. You're mentioning you have some machine learning or some AI in aiding for the designing. I would like to know a little bit detail what kind of algorithm for AI in helping for this kind of design. Okay.
I think the machine learning and AI currently I think are very hot. I think the one major reason I think there's a lot of fuel cell researchers, I think also researchers in general, want to apply machine learning and the AI into this kind of the fuel cell or other development. And we are working on some sort of the artificial neural network. This for the machine learning, let me go to this kind of slide here. And this one here. We're also working on this kind of genetic algorithm. And this is artificial intelligence. And to find the best, this the GA is like this kind of the genome selection. And they will, after generation, they will find the best and the value and to optimize the fuel cell operation or design. So I hope this answers the question.
Very exciting presentation. Thanks to Professor Wang's presentation. Our next speaker is Professor Wang from the Department of Electrical and Computer Engineering, University of Southern California. Professor Wu graduated from Peking University with a bachelor's degree in physics and received his PhD degree in electrical engineering from Princeton University. He is famous for his work in nano-imprint, laser graphite, and its multiple application. His topic today is Memristor-based hybrid analog to digital computing platform for mobile robotics. Professor Wu, next 30 minutes are yours.
Okay, thank you, Dr. Su, for the introduction. And I also want to thank our manager for inviting me here, giving me the opportunity to share our work. My name is Wu from USC, and today I'm going to talk a little bit about control of robotics. I think I switch. Thank you. Okay, machine learning, artificial intelligence is a very hot topic. We heard about this from the last speaker. And so we work on hardware. And from hardware point of view, and the hardware for artificial intelligence is basically an artificial brain, right? So since it's artificial brain, so let's look a little bit at a human brain. And the human brain has three parts. The cerebrum, the so-called big brain, cerebellum, so-called small brain, and the stem. Stem is in charge of heartbeat and breath. Who cares about those, right? And so now let's look at the big brain and the small brain. Big brain in charge of a lot of things, like logical thinking, something like this. And the small brain basically help us in balance. For example, I can stay here. And so brain is very complicated. And most people work on AI, they work on the big brain part because this is the most powerful, most interesting part. And however, for us, we want to start from something small, something easier, because 道德经说过，图大于其细为图难于其易，为大于其细，对吧？ So we want to start from something simple. So we want to start work on the artificial small brain first. So what small brain does? Small brain keep in balance. How can I keep in balance? Because first, and I have all kinds of sensors on my body and send the signals to my small brain. And my small brain will synthesize those information, and so the small brain can know whether I'm leaning to the left or I'm leaning to the right. If I'm leaning to the left, I'll try to push to the right to keep myself in balance. So basically two functions. One is the sensor fusion. The second is the control algorithm. And of course, for artificial small brain, what you want? You want to be fast, low power consumption, and if you have many degrees of freedoms, you want it to be parallel. Actually, for example, if you look at the robot, and those robots working look like a human, but when you look at it, you know it's not a human. Actually, the reason for it is straightforward, because the robot actually has much smaller degree of freedom than a real human. For a real human, we have much more muscles, much more joints, and so they look different. So actually, for those kind of requirements, actually this can be a perfect application for analog computing. And what is analog computing? People talk about analog computing, I think almost since the 40s. And basically, if you want to add two things up, instead of using the CPU to calculate it, for example, you can have one resistor have a voltage of 1 volt, the other has 2 volts. If you measure the total voltage, it's 3 volts, so you know 1 plus 2 equals 3. So basically, using some physical measurement to do the computation for you. And people actually talk about analog computing for many years, because actually it has some advantage. You don't need to analog to digital conversion, digital analog conversion, things like this. And everything happens really fast. It's just analog circuit, basic RC delay, everything really fast. So it can be very parallel, very fast, low power consumption. But we all know, people talk about this for many decades, still not happening. And the reason actually is very simple. There's the biggest advantage for analog computing is analog computing doesn't have enough precision. For example, for a digital computer, you can have as many digits as you want. So you can have it as precise as you want. But for analog computing, it's based on the measurement of some physical value. And so in the end, your precision is determined by your signal to noise ratio. And but on the other hand, for the application of artificial small brain, do we really care about the accuracy? No, we don't, right? And do I really care about I'm leading to left by 1 degree or 1.1 degree? No, we don't. So let's make it actually a perfect application for analog computing. However, actually, this is not surprisingly. Actually, about 40 years ago, people already proposed to use analog computing for robotic control. But if you look at the reference I'm citing here, the journal is called Mechanism and Machine Theory. So you know those are all theoretical papers. People never really implemented them. And what's the reason? Because there's no proper device to implement those hardware in a straightforward way. But recently, people discovered a device called a Memristor. And then this actually can be a perfect device to implement artificial small brain. And so this is the outline of my talk. First, we will have a quick introduction about what is Memristor. Then I will talk about the artificial small brain we built based on Memristor using analog digital hybrid computing platform. And Memristor is very simple. It's basically a two-terminal device. You have 2 electrodes, and you sandwich something in between. And because the ion move inside this switching layer, and then you can have either a high conduction state or low conduction state. Basically, if you form a conduction channel here, and you have a high conduction state, if the conduction channel is disconnected, then you have low conduction states. And also your conduction channel can be bigger or smaller, so you can also have a different resistance. And so it's just a two-terminal device, or just like a resistor, but the resistance value is changeable, and just by applying proper voltage or current through it. And so this is the device fabrication process. It's fairly straightforward. And this is the device we fabricate in our lab. It kind of shows we have many different conduction states. And for this specific device, we have 157 different states, and all like 7 digits. And this just show the last graph was too busy, so this just show we program this device to 10 different conduction states and equal spacing. And this is just the hardware, we can program it. And it's fairly straightforward. I am not going to go through details, but so those are the carriers for the device. So the chip will be here, and we have Arduino to control everything, and we just apply a series pulse, current pulse through the device in order to program into different states. Here is just the SD data logger. So when we program it, we store data here. So in the end, we can take the data out and write a paper back. And for real robot, we don't need that one. And I don't think you are interested in the detail of this, but here, basically what we are doing is we apply a current pulse through the device, and then we apply a smaller voltage to measure the device and to see the change of conduction states. And here actually shows 100 pulse, and for the first 50, we make the conductions higher and higher and higher, and for the next 50, we program it to lower and lower. And okay, so this is the device we have. And now let's talk about the real fun part. So we want to use this to implement the small brain of a robot. So we work on this is really the simplest possible robot. It's just a self-standing car. It only has 1 degree of freedom. So it's really the simplest one. And so here actually you can see this. This is the sensor and sensor fusion part, and this is the control algorithm part. And so this shows the system diagram of this self-standing car. It's basically a reverse pendulum. It's very, very simple. And so reverse pendulum, of course, what the sensor fusion need to know? You need to know what's the position, right? What's the angle? Then to tell the motor whether turn this way or turn that way, and how fast you want to turn it. And so the sensor fusion part will give you the information about the angle, and then we feed this information of angle information to the controller. and the controller will decide how much voltage you apply on the motor. And so this is basic system scheme diagram, and here system diagram. And then the first part that's a sensor fusion, and that's a controller, and then this is the signal sent to the motor driver, and just drive the motor. And so first, let's talk about the sensor fusion part. The sensor fusion part, we're using algorithms called the common filter. Actually, this is probably one of the most commonly used sensor fusion algorithm. Actually, it's very simple. And this actually was invented for Apollo project long time ago. And without this, people couldn't land on the moon. So and the common filter idea is very simple. So for example, you have a spaceship, and you want to know what's your position of your spaceship. So you do constant measurement. But when the space getting further away, the measurement will getting less and less accurate. So the errors will start to diverge. In the end, the error is too big. You cannot land on the moon anymore. But then the Dr. Common, very smart guy, and he realized, so there are two ways for you to know your position. You can either measure your position directly, or if you know your position, previous position, and you know your current velocity, and you can calculate what is your current position. And so now, actually, you will have two data. One is from the direct measurement, and the other is from a prediction. Then you can combine those two results together. And it's just like you measure something, you measure it multiple times, you can make it more accurate. It's basic idea. Then, if it satisfies certain condition, the error no longer diverge. So then people can land on the moon. And same thing here. And for our common filter, of course, we constantly measure the angles. So it's not a digital, it's not a discrete time, it's continual time. But the fundamental idea behind is the same. And so in our robot, and we have an accelerometer measure the angle, and we have a gyroscope, and the gyroscope measure angular velocity. So based on the previous angle and angular velocity, you can calculate what's your angle, and also you can measure your angle directly. And then when we feed those into a common filter, and then we can synthesize the information into more accurate measurement of our current angle, our current position. And actually, for the self-standing part, that has a digital common filter came with it. But actually, common filter itself, the calculation is very simple. The calculation itself is very simple. However, for the sensor, for accelerometer and the gyroscope, they measure what's they have a measuring value. They have to analog to digital converter, convert into digital information, then send through the communication bus to the processor. And the processor will do calculation. The calculation is super simple. Then it will send from the bus back. So there's a lot of overhead, especially in the communication channel. So for the digital common filter, it takes a few milliseconds to finish everything. And but here, actually, this is our analog circuit to do the common filter. Thank you. And so this is this is a system diagram, and this is our circuit diagram of our common filter. It's very simple. And so for a simple circuit like this, the delay is basically just RC delay. It's basically variable. It's less than 1 microsecond. So it's the latency from a few milliseconds decreased to 1 microsecond. Oh, by the way, in the circuit, we have one Memristor here to represent common gain. As I just mentioned, for the common filter, this you have a prediction value and you have a measurement value, and you combine those together to get the measure to get your value. And you have to add them up with different weight. And what determines the weight? Basically determined by the signal to noise ratio of each value. If this one is more accurate, you want to have higher weight on this one. If this one is less accurate, have a lower weight on this. So the common gain actually represents the weight. And so it's a tunable, and so we represent common gain in circuit using this Memristor, using different resistance value of this Memristor. And here actually is a movie, and it shows, you can see. So here on this robot arm, we have our sensors and the common filters here. And on the oscilloscope, you can see on the top, the noisy one, that's a direct measurement of your angle. And the bottom one is after common filter. You can see obviously it looks much more smooth and much less noise. And another thing, actually, when I show this results to some of my friends, he asked me, why can't you just, why do you have to use this exotic device called a Memristor? Why can't you just calculate what should be the common gain, calculate what should be the value of the resistor, and just put it in your circuit? Well, it turns out that, as we said, the common gain is actually determined by the signal to noise ratio of each sensor. And for sensor, exactly same model of sensor, the signal to noise ratio may not be the same. So for example, we bought from Amazon 4 different gyroscopes, exactly same model. And if we're using the same common gain put into the circuit, you can see only gyroscope 2 actually give us the perfect condition, and the general one will be undershoot, gyroscope 3 and 4 will be overshoot. So so that's why we want to have something tunable, and also actually the signal or to noise ratio of a device also depends on temperature. For example, for the same gyroscope, if the temperature is too cold or temperature is too hot, and we have to change our common gain in order to have the optimal performance. So now we have our sensor fusion. Now let's talk about control. The control part is super simple. Again, we only have one degree of freedom. It's really just a PD control. Simple is a type of control. And in the PD control, you have one parameter. That's a damping term. It's just, you can think like this. You have a spring, you have weight, and it can vibrate. You pull the spring, the weight will vibrate. And it take a while to go back to balance. And of course, if you put your weight inside, for example, water, you have a lot of damping, then it won't vibrate too much, right? But if damping is too much, for example, not water, you put in some very viscous liquid. And then again, due to the damping, it will take a long time to go back to the balance. So you want to have a proper damping in order to make it go back to balance the quickest. And this term actually to be tuned in the circuit. And here just a system diagram, and we also using an analog circuit to do the PD control part. Instead of you send the angle information to the digital processor, and for the processor calculate what you should do. We just make a simple circuit and to do the implement control. Then again, it takes almost no time, just a RC delay. And of course, we have to tune the Memristor to have a proper damping. And here you can see our Memristor has different value. And for some value, it's very longer time. For some value, it's go back to balance quicker. And of course, to set the proper value, we also want the robot to be able to learn to stay in balance by themselves. And because, so imagine you have a robot. If the robot hold a box, or without holding a box, of course the system function will be different. Then the parameter needs to be different. So we hope the robot can learn by itself. And so how we do it, actually, again, is super simple here. What we do is, so the damping term, and in the damping parameter in the PD control is represented by the conductance value of our Memristor. And then in the circuit, we just put another small resistor in serial with our Memristor. And then the small serial resistor can be either bypassed or not bypassed. So if we bypass it, the resistance value is the same as Memristor. If we don't bypass it, then the resistance value will be slightly larger than Memristor. So for every scenario, we will do 2 measurements, and to see which one is more stable. And of course, we will have the same impact. Actually, I will show you a movie to see. You can see how we did it. Basically, we have an apple to hit on the self-standing arm, and then to see how much time it takes to go back to balance. And then whichever is more stable, then if the lower resistance one give you more stable scenario, then we will tune the Memristor to smaller resistance. If the higher resistance value make it more stable, we'll just tune the Memristor to higher resistance until there's almost no difference, then we stop. And actually here it just shows, this actually just shows angle of after 17 times training, And after the impact, how the angle changes, it go back to balance much quicker and very stable here. And the black, this is the red one. And the black actually that's from the original digital platform. And it will take much longer time to go back to balance. And this is zoom in view. And actually, those are the real data. Shows each measurement, how it learns to balance itself, and we tune the conductance value of Memristor after those. And at here, you see the lower conductance and higher conductance one have almost the same performance, so we stop the tuning. So pretty much, we think we reached optimal. And I don't think you're interested in this, but this is a circuit diagram of a control part. But actually, very simple. And here, that's two Memristor, one for the common filter and one for the PD control. And the top part, actually, that's just a tuning circuit to tune the conductance value of each one. And the bottom part, this is actually the sensor fusion circuit. This is PD control circuit. Others is just like a motor drive kind of things. And of course, you always need to compare with other technology. I don't think you are interested in this, but basically, our technology is much faster and consumes much smaller energy. Oh, you think about it. There's no such fancy stuff, no communication channel, everything just a small analog circuit, of course. But of course, I've been bragging so much, so you may not believe me, so I will show you a video. And so here you see the video on the top. Oh, that's the self-standing car with the hybrid computing system, the analog and the digital computing system for the small brain. And the bottom one, that's the digital one, coming with the self-standing car. And we are going to use Apple to hit this one. So we will put Apple to the same Apple to exactly same height. So every time the impact is exactly the same. And then you will see what will happen to both cars. They are the exactly same car. We just replace the control part, the sensor fusion and the control part. Everything else are the same. And this is 8 times slow motion, and you can compare those. You see the top one go back to balance immediately, but the bottom one is shaking for a while, right? And I will play it again. I want to pay attention to the wheel. You see, after the impact, the top one, the wheel starts to turn immediately. But in the bottom one, if you look very, very carefully, you can see a teeny tiny delay. After impact, it takes a little bit time for the bottom wheel start to rotate. And this is why the bottom one shakes much more, right? And the basic reason is really because for our system, the delay, so for the digital one, the delay is in order of a few milliseconds. The latency is about a few milliseconds. For us, the latency actually is, I think totally something like 4 microseconds. And because of this, okay, so what's our next step? Actually, right now we'll continue on this track and basically work on 2 fronts. One, we are working on more complicated robotic system with more degree of freedoms. For example, like this micro drone. And another thing is we are also working on to integrate heterogeneous integration of Memristor and the real silicon chip. So integrate them together instead of put them on this printed circuit board. Now we will actually, in the end, we will just have a chip and the chip coming out of TSMC. Then so we will do the last step to add some Memristor on top of the chip and do the sensor fusion and the PD control for more complicated robotic system. And those are the 2 students did the most of the work. And the work was sponsored by IAPA and the Air Force Research Lab. And of course, I also want to thank my collaborators, Professor Wang and Professor Yang at USC. And of course, last not least, and thank you.
Very, very wonderful speech. And significantly, Professor who also not only have an excellent brain, but also have a very excellent small brain. He can keep the balance. You can keep the balance. So we have the timing. We have only time for 2 questions. Any question? Only two?
Yeah, thanks for the talk. It's very interesting because I'm wondering whether there's any generic analog computers available in the market. Because digital computer, the advantage is that the generic, like microcontrollers in the market, you can easily buy with like $30. But how about if I want to teach my kids at home, to play with it, I will not be able to find anything. What's the market looks like right now?
Okay, great question. And first of all, digital computers is so cheap, and because everyone uses it, right? But there are some applications. For example, actually, I specifically showed this micro drone. That's actually one of the projects we are working on. One of the problems is this: for a system like this, you have more degree of freedoms. And then simple PD controller no longer works. People typically using something called a model predictor control. What's that? So you have a system model. And so the drone think I should be at this state, but you do a measurement. And then this is your real state. Your real state and the state you want to be won't be the same, most likely. So you have to do something right to crack it. And this is actually become an optimization problem. And the optimization problem in digital computer actually can be very time consuming. Actually, for the more complicated controller, digital controller, the MPC, model predictor controller, 95% time actually consumed is in this solving optimization problem. And right now, actually, we are working on a circuit. Actually, we just gave a conference talk 2 weeks ago, and we're using analog circuit can solve this optimization problem in almost just as a delay. And of course, the precision may not be as high as the digital one, but it's super fast. And it consumes almost no computing power. And the reason we work on this is that the government gave us money to work on this because for things like this, there's only 15 gram payload. And because it's so small, they just cannot afford to put in any decent digital computer inside. And for those kind of things, now actually people talk about IoT, right? IoT is small device, low power consumption device. So those actually can be, so it's 1 and 0. So those can be a good application of this. And the second thing is, right now, well, it's, you cannot buy it because there's no demand, right? And so it's a chicken and egg thing. And so the IoT market is huge. And eventually, all the small IoT devices, they all want to have some type of low power controller. And then that's something we obviously we can do, right? And probably there will be some type of protocol, and people, everything all certified on this. And so you can make something more generic one, and you need to tune, for example, one of the 2 parameters to fit your own application. Then I can imagine if you have enough market, the price may go down.
Only one more question. Okay, thank you, Professor.
Thank you.
He is President of Water Supply and Water Resource and Chair of Chemical Committee of Groundwater Resource Association of California. Dr. Singh is a registered California professional engineer with more than 17 years of research and consulting experience in the areas of water resource planning, management, hydrologic modeling, build and uncertainty analysis, optimization techniques, geographic information systems, and data analytics. Dr. Singh's topic today is the importance of recycled water, recharge, and use for Southern California, past, present, and future. Dr. Abhishek.
Thank you, Mr. Su. Thank you. Sue. It's great to be here. I wanted to just start by thanking the Chinese American Engineers and Scientists Association Southern California for having me here. So I'm representing two organizations here. My name is Abhishek Singh. I'm Group President of Water Resources and Supply within Terra, but I'm actually representing the Groundwater Resources Association of California. So I'm kind of speaking on both behalves. And I'm going to be talking about recycled water. So we've talked about hydrogen fuel cells and analog computers and robots. Now we're going to look really big picture, kind of expand the focus and talk about something that's an issue statewide. So talking about water resources, sustainability, resilience, and how we're using recycled water. I'll focus in Southern California, but these implications are statewide. So just a roadmap of my talk, I'll give an overview of the professional organization I represent here, the Groundwater Resources Association of California. Talk about California hydrology and water resources, set the stage of why it's important to talk about recycled water and how we're using it in Southern California. All of you are touched by this issue. Actually, I think the City of Industry, where we're having a conference, most of the outdoor water use is recycled water. Talk about indirect potable reuse. So indirect potable reuse means using recycled water for drinking water purposes. So what are the regulations? How do we design engineering systems in California to allow for recycled water to be used for drinking water purposes? Touch on two case studies in Los Angeles, in the Los Angeles County, and then talk hopefully we have time for questions. All right, so the Groundwater Resources Association, we turned 30 this year, so it was founded in 1992. We're a professional organization that drives towards sustainable groundwater for all. We're primarily focused on education and technical leadership that leads to resource management that protects and improves groundwater supply and quality throughout the state of California, although now we've expanded our focus and looking at pretty much all of the United States. We have more than 1,000 members. From industry, government, academia, research, and the general public. So if you care for the environment, if you care for water, groundwater especially, please think about joining GRA, the Groundwater Resources Association of California. All right? Some of the things we do: professional development of scientists, inform statewide policy on groundwater management. We have a scientific magazine called Hydrovisions. So go out and check our website. But essentially what we're trying to do is influence future technical innovations and groundwater policy in the state of California. So that has a really good tie-in with the theme of the event today, which is innovation. And as I mentioned, we turned 30 this year. Our strategic priorities, this is very sensitive. Continue to lead in groundwater, build our organization's resilience, and expand and engage members. And this is the reason why we really appreciate the opportunity to be here. I've got two colleagues from GRA here, Moises, who's in the audience, and YR. So if you're interested, please reach out to us and we'll tell you more. Awesome. All right, we had a bunch of events here, conferences focused on aquifer recharge, groundwater sustainability. We have a pretty big event coming up in September 2022, which is the Western Groundwater Conference. It's going to be held in Sacramento. So yeah, that's our website. Check us out. Connect and follow on LinkedIn. And if you're interested, and you don't have to be a groundwater professional, if you're interested in the topic, you're more than welcome to join one of our committees: technical, legislative, diversity and inclusion, events, education, affiliates, or membership and communication. All right, so with that intro, I'm going to jump into the meat of my presentation. So, as I mentioned, I'm going to talk about water reuse in California. But before we understand why that's important for the state, it's important to understand, what is the hydrology of California? What are the water resources that we're looking at? I moved to California about 7 years back, and I was completely blown away and astounded by how complex our water system is. I don't think I would be exaggerating when I say that California may have one of the most complex and engineered water systems in the world. I think we compete with Israel on that front. California is the 5th largest economy. We're trying to find water for 39 million people. I think close to 40 now. We have 5 million acres of agriculture in the state. We're the food basket for not just America, but for countries outside as well. We have about 40 million acre feet. Now, the acre feet is a term that you'll be hearing a lot. Acre feet used to be the amount of water that an average household used in America, but now because of conservation, it's much less. In an acre feet of water is think of a football stadium, and if you fill it with 1 foot of water, that's about an acre foot. And it now, with conservation, it's enough water for anywhere from 1 to 2, sometimes 3 households, right? So 40 million acre feet of water is enough water for 80 million households. That's how much water we're talking about. Highly engineered system. A lot of the water is tied up in litigation and adjudication, so it's a complex interplay between policy and engineering and law. Groundwater, which is the mission of GRA, is about 40% of the state water supply in an average year. In a drought year like this year, it's much higher. It could be up to almost 50%. And because of the over-reliance on groundwater across the state, we're seeing depleting groundwater supplies. So this is just a graph that shows the reduction in groundwater storage across the state, and it leads to all kinds of unintended consequences, like you've got subsidence problems in the Central Valley where the ground is sinking, I mean tens of feet over the last 50 years, almost 30 feet in certain areas. So it causes all kinds of issues, and of course, as the supply goes down, you can imagine that we're getting, we just have less groundwater to tap into during drought years. So this is a very critical issue for the state. California has a Mediterranean climate. There are very few places in the world that actually have a Mediterranean climate, apart from the Mediterranean, of course, South Africa, parts of Australia. And basically these are characterized by 2 aspects. One is that most of the rainfall happens in the winter months. We don't get a lot of storm, we don't have monsoons, for example. I come from India, I grew up in India, and there, of course, in the summer, you have the monsoon rains. And this is important because think of when you need water the most. You need it in the summer. In our state, as other Mediterranean states, most of the rain comes in the winter, when you need it less. And in California especially, most of the rainfall is in the north of San Francisco, and in the east, in the mountains, the Sierra Nevadas, of course, where it becomes snow. But think of where most of the demand is. We've got this, Los Angeles and the greater Los Angeles area, we've got millions of people. So our demand and supply centers are a little offset. California water hydrology is driven by ENSO cycles. So these are you hear about an El Nino year or a La Nina year. And these are years where, you either have more or less precipitation. We're currently in a La Nina year. It's looking like it's going to, continue to be a La Nina year through the rest of this year and maybe next year as well. And so what this causes is there's a lot of interannual variability. There is really no such thing as an average water year in California. You either have very wet years or very dry years, all right? So you also have an issue with timing. And so this is just an example. This is the same spot in 2015. In the Sierra Nevadas, when Governor Brown was actually out there measuring snowpack, as you can see, there's no snowpack, right? So this is in the mountains, foothills of the mountains. And in 2017, which is one of the wettest years we've had in the last decade, we got the Oroville Dam almost, reaching. You got, tens of feet of snow at the same location. 2022 is looking pretty grim. We've had one of the lowest snowpacks in the Sierra over the last 50 years. So along with this variability, we also have very high water use in Southern California, of course, because that's a big urban center, but in the Central Valley where we grow most of our crops, right? So that's a big agricultural center. And so what California has done, and this has really driven growth and development, and I mean, it's made California the 5th largest economy in the world. What we've done is we have a highly engineered system of connecting the dots. We take water from where it's available and we convey it and store it in areas where it's needed. So it's a demand and supply connection across the state. We bring water all the way from the Delta near Sacramento down to Southern California. The water is used to feed agriculture in the Central Valley, through the Central Valley Project. We get water from the Colorado River that feeds, San Diego, parts of Los Angeles County as well. And so we're getting water from these different areas, connecting it to the demand centers, and then managing the timing and the location. So it's a very complex storage and conveyor system. It's also aging. We need to upgrade this infrastructure. So I'm not going to talk about that, but that's part of the issue that we're facing in the state. And what's happening with climate change is that we see a shift in the seasonal patterns. We're seeing less snowfall. The timing of snowfall in the Sierras is changing. We're seeing hotter temperatures early on. So, and the important thing about snow and ice is that it acts as a storage account, right? You can store water in the Sierras. It melts over time through spring that feeds our rivers and gives us water for drinking water purposes, for environmental purposes, as well as for agriculture. So that timing is shifting. We're seeing less and less snowpack in an average year because a lot of that water is now liquid water. And then because of higher temperatures, there's also more evaporation. So we're also losing more water, right? So what used to be kind of a storage account has now become a checking account. You just get the water, it flows out, you gotta capture it, and you gotta use it, or else it's gonna flow into the ocean. Right? So this is a statewide phenomenon. This is just a graphic showing reduction in snowpack over the years. We're projecting almost 65% loss of snowpack by 2070. So over the next 50 to 75 years, we're going to be losing more than half the snowpack that we have in the Sierras. So that is what I call the California conundrum. Water supplies are typically not where and when they're needed. Conveyance and storage is required, but it's expensive. Climate change is shifting the timing and the type of available water. I get asked this question a lot. What about ocean desal? That's the solution to all our problems. But ocean desal still is very expensive and extremely energy intensive. And if we need to fight climate change, we cannot be switching to a water source that is very energy intensive. So maybe once we have more green energy, the hydrogen fuel cells that we're using for cars, maybe you can use that to desalinate ocean water. This might become an option for us. So conservation and reuse is really key to us building a resilient portfolio. So this is what brings me to the importance of recycled water in California. So reclamation is taking water that has been, has either been impacted or environmentally degraded and reclaiming it, so cleaning it up. Recycling, using that water over and over again, and reuse, where you take water that has been used and then clean it again and put it back into use, are key to water security in California. As you can imagine, recycled water reduces vulnerability to drought. You still have that water, if we can reuse more of the water that we're consuming, we'll be less reliant on rain or snow. It's resilient to climate change. In Southern California, as I mentioned, we get water from Northern California as well as the Colorado River. We refer to these as imported water supplies. So with water reuse, if we use local water, we recycle local water, we are less reliant on imported water, and so we have a much more robust portfolio. And there are also several economic, energy, and environmental benefits. California actually has a long history of recycled water. Our state was the first state in the United States to regulate the use of recycled water way back in 1918, and this was for agricultural use. This is for drinking water purposes. So we've been doing this for about 100 years. The state also leads the country in terms of regulating recycled water, putting out regulations to keep our drinking water supply safe. And so because of that, we've seen some pretty astounding growth. So this is a curve here that shows the growth of recycled, actually this is water reuse in California from 1970 to 2020. And you see almost exponential growth all the way to 2015. And what happened there was that we got hit by the drought. And when you have drought conditions, you just have less water to recycle and reuse. So we see a little bit of plateauing, but we have some very, very exciting projects that are pushing to increase the amount of recycled water that we're using. So we've already seen exponential growth, and we have some very, very ambitious goals statewide. So that graph on the left, we're planning to almost double our recycled water use by 2030. We didn't quite meet our goal of 1.5 billion acre feet in 2020. I think we were about 1.2. So if the state trend continues, we're looking to double the amount of recycled water in the state. All right. So I talked about potable reuse, and what potable reuse means is using recycled water for drinking water purposes, all right? So right away you can imagine that there are safety concerns. You want to make sure that, and so what, this is water coming out of our houses, going into treatment facilities, and so the state has defined a regulatory framework for the reuse of water for drinking water purposes. And currently the only way you can use recycled water for potable purposes is what's called indirect potable reuse. So it's not direct potable, what's called toilet to tap. We're not quite there yet, NASA is. But California regulates this through the process of indirect potable reuse. And what that means is you take treated wastewater, water coming out of wastewater treatment facilities, and you push it through an environmental buffer. And so in California, in Southern California, this environmental buffer tends to be the soil, the subsurface, the groundwater aquifers that we are standing over. And what this does is that in addition to, of course, the water is advanced treated, so it's treated down to drinking water purposes, but it does two things. One is the soil aquifer itself, filters out bacteria and viruses, and there are, biological and chemical processes that make that water safer to drink, right? That's why groundwater has less dissolved solids, has less bacteria, and so on and so forth. And the other thing it does is if there is some kind of a disruption in treatment, you have a buffer. Before that water hits your drinking water supplies, it's been in the aquifer, we have to monitor it, we have to sample it, so you know before it impacts your drinking water supplies that something has messed up the treatment processes, and you can manage that. In 2019, I believe, California also permitted the use of surface reservoirs. So that is where you take this water and put it into a surface reservoir. Now it still has to sit there for a certain amount of time. It has to have a residence time in that surface water body before it can be used. This is not common. The most common are using treated water for surface spreading, where it just percolates into the ground, or using advanced treated water and injecting it into the groundwater basin. So this is a map that shows locations for different types of potable reuse projects. So I'm going to step over here. As you can see, you've got projects that go all the way from what I call groundwater augmentation. So we're taking water, treating it, injecting it into the ground. There's some planned reservoir augmentation projects. These are the newly permitted projects. I believe that the Central Coast has one. And then where we're headed towards is direct potable reuse, where you can take that treated water. Of course, it's advanced treated. It's treated to drinking water standards, and put it right back into your drinking water distribution system. So that would be direct potable reuse. And there is upcoming regulations that the state has been pursuing to get to that endpoint. Overall, if you look at the total balance of recycled water in California, potable reuse, using that for drinking water purposes, is about 20% of the overall portfolio. All right? So it's important, it's growing. And as you can see, the cluster of potable reuse projects are really in Southern California. So why is that? Three reasons really. For there to be reuse, there has to be use in the first place. So this is high population area we use a lot of water, and so there is we have the opportunity to reuse it. There is water demand, and so that water reuse can be put back into urban systems and can feed drinking water demands. And most importantly, there is a revenue base, right? So there are the water districts and water agencies and municipalities that collect taxes, and those go towards the development of these large engineering projects. Water reuse, water recycling is less expensive than desalination, but it is still expensive. It's not, it may not be an economically viable option for agriculture. Because again, like in the Central Valley, you need to build treatment systems, you have to treat it to the advanced treatment side of things, and we don't have that, those kinds of cost economies. So the indirect potable reuse is regulated by the State Water Resources Control Board. So I think YR, if he's still here, is from the State Board, right here. So if you're interested in more of these regulations, I'm sure YR can give the next talk on that. But basically, the state is trying to achieve two different objectives. One is we want to increase the amount of recycled water that we're using in the state. But we also want to make sure that this recycled water keeps our drinking water supplies safe. So the state board is leading the effort to meet the state's very ambitious recycled water use goals, but it's also invested in enforcing the Clean Water Act and the Safe Drinking Water Act, right? So we need to use more recycled water, but we need to do that while keeping our water supply safe. The Regional Water Quality Control Board and the Division of Drinking Water coordinate the permitting. So the Division of Drinking Water is a special division that just focuses on drinking water. And then if you're interested, I don't need to go into all of this, but the production and the use of recycled water is coming from the California Code of Regulations, what's called Title 22. So oftentimes this water is called Title 22 water for that reason. All right, so I'll just give you a quick overview of what are some of the regulatory drivers here. As I mentioned, advanced treated water, and you can't use just secondary or primary or tertiary water for that matter. It has to be advanced treated. That means reverse osmosis or some sort of oxidative treatment processes that are necessary to remove all bacteria and viri. If you're using, if it's a surface application, if you're just putting that water on the ground and letting it percolate, you can actually use tertiary water. And tertiary water is basically where you use chemical processes to dechlorinate or use ozone. It's still not ready for drinking water purposes. So if you're just spreading it on the ground, you can use tertiary water. But if you're injecting it into the groundwater basin, you have to use advanced treated water. The aquifers I mentioned acts as an environmental buffer. So this is an example where that treated water is being injected into the ground. It goes into the aquifer and moves towards drinking water wells. You've got to have a lot of monitoring to make sure that water quality is good, is safe. So there are some very stringent requirements that the state has set, both on the treatment side as well as the monitoring side. So for the scientists out here, basically the state requires orders of magnitude of reduction of pathogen load in the water. So you need to demonstrate that through your treatment processes or through the residence time in the aquifer, you're reducing viri by 12 logs, right? So that's several orders of magnitude, and bacteria by almost 10 logs. And you can use the underground retention time for this treatment process. And the main goal is to prevent treatment failure from contaminating drinking water supplies, because that would be a total catastrophe. A project is required to demonstrate response retention time in between wells. Again, this is a bit of a technical term, but think of it this way. We're trying to account for any potential treatment failures in your system. And so what you need to make sure is that the time between injecting or introducing that water into the ground and the time that you take it out of the ground, you've got at least a month or several months between those two events. And that is to monitor for any treatment failures and respond to those. That's why it's called response retention time. All right, so I'm just going to very quickly run through a few case studies. We're in LA County, and you're surrounded by recycled water projects, and these are just a few examples. I've shown a few example projects in LA County as well as Orange County. We've got what's called the West Coast Basin Barrier here, and there are a string of injection wells that take recycled water, inject it into the ground, and they actually serve two purposes. They protect the aquifer from seawater intrusion. So with sea level rise and groundwater levels going down, we have the potential for seawater to go into the aquifer. So they protect the aquifer from seawater intrusion, but they're also taking recycled water, injecting it back into the ground, and increasing the yield of that aquifer. We have three other gaps all along the coast: the Dominguez Gap, Alameda's Barrier Project, and then the Talbot Barrier, which is further south. Moises is from the Water Replenishment District. I'm sure he'd love to talk about the barrier projects here. They're all run by the Water Replenishment District of Southern California. And then in Orange County has very, I think it's one of the largest in the world treatment facilities, GWRS, and they're using that to recharge their water as well as maintain the yield of the basin. So I mentioned the West Coast Basin Barrier Project. This runs all the way just south of Santa Monica, all the way to Torrance. Most of the wells are subsurface, so you're not going to be able to see them. But there are 153 injection wells that were built between 1950 and 1960, all along the coastline, and they use a blend of recycled and imported water. The imported water is coming from the Delta. I think they mostly use Delta water. I don't think any Colorado water comes to the barrier. And as I mentioned, they protect the aquifer as well as recharge the aquifer to prevent overdraft. And this is how we managed to keep the aquifers, to keep the groundwater in balance in much of the greater Los Angeles area. And so what we do, and what I do as an engineer and scientist, this map here is showing a map of these are actually chloride concentrations. So this is seawater concentration in the aquifer. And the highs are higher concentrations, the cooler colors are lower concentrations. So you can see how the barrier is working to keep the seawater at bay. It's not letting it enter into the basin. And that's very, very important for our drinking water supplies. I live in Torrance. This is the water that I drink. So what I do as an engineer and scientist that I was going to mention was we build computer models to simulate what's going on with the aquifer, what's going on with the water quality. And we use that to design our projects to ensure regulatory compliance. We look at how much time it's taking for that water to reach the drinking water supplies. What is the best area to put those injection wells? How long can we continue to pump at what concentrations and so on and so forth. And there's a lot of reporting to the regulators. And right now there are plans for barrier well replacement and additions. Another facility which is shown right here, advanced treating it and piping it all over and using it to recharge the basin. It's also being used for non-potable use, so for non-drinking water purposes. With this project, Los Angeles is looking to maximize the production of recycled water from the treatment plant, but most fundamentally improve water supply resiliency and reliability of Los Angeles. They have very ambitious goals to go completely off imported water. And this project has been done in partnership of LADWP and WRD, that Moises is from. We're looking at 24,000 acre-feet of injection and extraction facilities, 20 injection wells, 12 extraction wells, and again, we've used a lot of models and data to design the project and look at the feasibility and the environmental impact. So with that, I'll conclude. As I mentioned, indirect potable reuse of recycled water is a critical and growing part of California's water supply. California regulations are meant to balance the need for indirect potable reuse with ensuring safety of drinking water supplies. The aquifer or the soil really acts as an environmental buffer, and we use a combination of very high-end computer models as well as data that we're collecting from the field to manage, to design and manage these projects. California has ambitious plans for IPR and is moving towards direct potable reuse. That regulation is upcoming. And IPR is particularly important in Southern California due to our high water demand. vulnerability to drought, and the existing and future IPR projects in LA and OC. Riverside is looking at a few projects. San Bernardino County actually has a very, very ambitious project, almost 10,000 acre-feet of recycled water injection. And those are going to be key to improving our water resiliency and reliability. So with that, I'd just like to acknowledge the agencies I work with, GRA, and of course, all of you for your attention and for the invitation for this conversation.
It's a very wonderful speech. Because the time, we can only have time for one question. Okay. Okay, you first.
Well, next talk probably is a stupid question. Why do you have to inject recycled water into underground? Why can't you just dump it to a lake, for example?
That's a great question. So, as I mentioned, now California does allow for surface water augmentation. Let me I think it's the slide right up. So we do have the option of surface reservoir augmentation, but the primary reason why subsurface augmentation was permitted first is because the residence time is much slower in porous medium. So that water is going to sit underground for much longer, whereas if you put it in a lake and say there is a treatment failure, you have an immediate impact on aquatic habitat, or if you're using that lake for drinking water purposes. So we do have that permitted now, but the norm so far has been on the subsurface side, but things are changing. I think we're looking, as technology improves, as we're doing more and more monitoring, we're going to move towards more direct uptake of recycled water. Yeah.
Thank you. Very good. Because the time limit, we cannot answer any more questions. If you have any more questions, please ask Dr. Singh later. Okay. Thank you. Thanks again to all the speakers this afternoon. Thank you so much for taking the time and sharing your stories and insights with us. Words are powerless to express our gratitude to your fantastic and knowledgeable presentation. So all the speakers are welcome to join the evening events with a free ticket.
We'd also like to thank all our audience for joining us in our forum and symposium today. And we have more programs coming up this evening, so be sure to come back at 6 p.m. We'll feature 3 keynote speakers and award ceremonies in the ballroom.
We hope you all enjoy the dinner, and we will see you in an hour. Thank you. See you later.
Thank you very much. And please, all the speakers for the technical symposium, if you could come to the stage, we're going to have a group photo together. Thank you.